brief introduction to batteries, a collaboration between Beyond Benign and IUPAC. Batteries power the modern world, from smartphones and laptops to electric vehicles and grid-scale energy storage. But what is a battery, and what chemistry allows it to store and release energy? At its core, a battery converts chemical energy into electrical energy using controlled redox reactions. These reactions occur at two electrodes, the anode and the cathode, separated by an electrolyte that conducts ions but not electrons. Let's start with the anode, which is the negative electrode during discharge. In most lithium-ion batteries, such as those found in phones and electric vehicles, the anode is made from graphite, a layered form of carbon. Lithium ions can reversibly insert between these layers by intercalation, while electrons are transferred through the external circuit. The cathode is the positive electrode during discharge and is typically a lithium-containing transition metal oxide or phosphate. Common examples include lithium cobalt oxide, lithium iron phosphate, and lithium nickel manganese cobalt oxides. These materials are chosen because the transition metals can undergo reversible changes in oxidation state while maintaining structural integrity. During discharge, lithium ions move from the anode to the cathode through the electrolyte. Electrons are released from the anode to maintain charge neutrality as positively charged lithium ions leave. The electrons flow through the external circuit to do useful work before arriving at the cathode and reducing the transition metals. Charging the battery reverses this process, reoxidizing the transition metals at the cathode. Despite their sophisticated design, sadly all batteries slowly lose capacity over time. One major cause is the formation of the solid electrolyte interface, or SEI, on the electrode surface. This thin layer forms when the electrolyte reacts during early charge cycles and is made of organic molecules and lithium salts. While the SEI is essential for stabilizing the electrodes, it continues to grow over time, consuming lithium ions and reducing the amount available for energy storage. Electromaterials also degrade mechanically. Repeated ion insertion and removal causes volume changes, leading to internal stress and particle cracking. Over many cycles, this can lead to loss of electrical contact and reduced capacity. But researchers are studying this to design the next generation of batteries. Some next-generation batteries offer entirely new possibilities. Sodium-ion batteries use sodium instead of lithium as the charge-carrying ion. Because sodium is abundant and widely available, this chemistry is especially attractive for large-scale energy storage, such as storing electricity from wind and solar power. All solid-state batteries replace the liquid electrolyte with a solid ion conducting material. This enables new, safer battery designs and allows the use of lithium metal anodes, which have one of the highest theoretical energy densities of any anode material. These emerging chemistries show how changing just one component of a battery can unlock entirely new applications. From redox chemistry and crystal structures to degradation mechanisms, batteries are a powerful example of how fundamental chemistry underpins modern technology. Continued advances in battery materials will be essential for longer-lasting devices, cleaner transport, and a more sustainable energy future. If you would like to learn more about some of the research which goes into developing these technologies, a webinar recording is available via the QR code. Thank you to Beyond Benign and IUPAC for supporting the production of these videos.